So here we have a diagram of sort of what's happening when light passes through the diffraction grating. Here you can see the slits. When light passes through the slits, it diffracts at a certain angle, and the angle at which it diffracts decides whether these waves will constructively or destructively interfere. When it constructively interferes, we get these maxima, you can see here, and they happen at very specific points, and there's like orders. So the 0th order, 1st order, and 2nd order. Due to Bragg's equation, which is here n lambda equals d sine theta, and because we were using a sodium lamp with a specified and known wavelength, we could work out from the angle of diffraction what the diffraction, what the spacing for the diffraction grating was. So once we knew D, we could repeat the experiment, but instead using a hydrogen lamp, which had multiple wavelengths.
Looking at the angles produced by the hydrogen light and then using Bragg's equation, we can find the wavelengths of the Balmer series transitions.
As we now know the wavelength, we can use the Rydberg equation here to establish what the Rydberg constant is. Here, the Rydberg equation is that 1 over the wavelength is equal to the Rydberg constant times by 1 over the final electron state squared minus 1 of the initial electronic state squared. Now this section here is known to us due to the Balmer series, so we have specific numbers for NF and NI. So using that and the wavelength that we calculated, we could work out the Rydberg constant.
Modern spectrometers, which use visible light and UV to accurately observe the lattice parameters and materials. These machines, like the one here, can cost upwards of 30 grand.